Hello everyone, welcome to this lecture. In the last lecture we studied FRF estimation using random excitation signal. In this lecture we are going to look at FRF measurement with a shaker using random excitation. So we are going to simulate the process of FRF measurement on a cantilever structure, and the objective is to study the various steps which are involved in the process of FRF measurement. So what we are going to show are simulated results. So these are not actual measurements, but these are the results based on the simulation of the whole process of FRF measurement with a shaker, okay, on a particular structure. So this is the test structure we are going to take. It is a cantilever beam structure, and it is basically of rectangular cross section, and the length, width and thickness of the beam are 50 centimeter, 5 centimeter and 3 millimeter respectively. So this is the test setup we are going to use. So you can see we have a shaker fixed here, okay, and then we have an accelerometer, right, which is used for response measurement. And in the lecture on FRF measurement using impact hammer, we have discussed in detail how the number of measurement points or number of test points are selected, how the frequency range and time domain and frequency domain parameters are selected for measurement, how the location of an accelerometer in a roving hammer test and the location of an exciter in a roving accelerometer test are decided. So all that discussion is also valid for FRF measurement using shaker. So therefore in this particular case we are going to use 5 number of test points, right, and then we are going to conduct a roving accelerometer test, and then we are fixing the shaker at test point 5 as shown in the figure. And then we are going to measure FRFs in the translational directions at these 5 test points, right. So we are going to take measurement in the translational direction like this and take the and measure the FRF along these directions, and a force also is applied by the exciter along the translation direction. So let us now choose the time and frequency domain parameters. So let us say we are interested in the frequency range of 400 hertz. So 0 to 400 hertz is the frequency range of measurement, and we have now chosen 5096 number of samples in the time domain. And we have studied earlier that out of the all the frequency and time domain parameters, we need to basically choose 2 of the parameters, and if you choose 2 of the parameters, then the rest of the parameters get decided. So these 2 parameters we have chosen, and now rest of the parameters defining the time and frequency domain, they get basically fixed. So let us look at those parameters. So this table shows various parameters of the time and frequency domain. So you can see we have now a sampling frequency of 1024 hertz, right, which is 2.56 times the F max, that is the maximum frequency range of measurement. Then FC, which is the cutoff frequency of the anti-aliasing filter, it is 512 hertz, right, and then we have taken a record length of 4 seconds, okay. So and then the resolution in the time domain or the time step, it is 0.0009765 seconds, right, and then we have a frequency resolution of 0.25 hertz, correct, and then we have number of frequency lines in the frequency domain is 1600. So these are the number of discrete lines at which the spectrum would be available. So these are the various parameters of the time and frequency domain. So with shaker we are going to use a random excitation signal. So this random excitation signal can be generated to excite a certain band of frequency, okay. So therefore with signal generator we can generate such a signal. So therefore we use a signal generator to generate a random voltage signal of 5 volt RMS amplitude, and the frequency range of this voltage signal is from 0 to 400 hertz. We also add some small uncorrelated random noise in the input and output to simulate the process of measurement, in which also some amount of random noise might be present. Now this signal from the signal generator is fed to the power amplifier, and now we have taken a gain of 1 volt per volt as the gain of the power amplifier. and then the output of the power amplifier is delivered to the shaker. So now we are going to use spectrum averaging, right, also for the FRF measurement. So several averages would be taken and then the FRF would be based on those averages. So let us first of all measure the FRF without using any window function, which means that we are going to use a rectangular window function, okay, as we discussed earlier. Not using any window function amounts to using a rectangular window. So let us now take the measurement of the force and acceleration, right. So let us look at what is the force that is transmitted to the structure, right, which is measured by the force transducer, and what is the acceleration at test point phi, right. So these are the time histories of the force and the acceleration signal. So on the left side of the figure we see the force time history, right. So we see that the force is random, so it is varying in a very random way, a very irregular way, and so it also generates a random response. So right side of the figure shows the acceleration at test point phi, and the record length is 4 seconds. So now let us look at the auto spectrum of the force, which is GFF, right, and also look at the cross spectrum between the force and acceleration, which is GFA. So the left figure shows the auto spectrum of the force, okay, and of the frequency range of measurement is 0 to 400 hertz, and the right side shows the cross spectrum between the force and the acceleration. So we should see that in the force spectrum, auto spectrum of the force, we see the force is not constant throughout it drops to low values at certain frequency. That is because of the force dropout phenomena we studied earlier, right. So now we take several such measurements and then perform spectrum averaging, and which gives us the point inertance. So we are going to look at the H1 estimate of the point inertance, and we are also going to see the coherence, right. So here you can see the upper figure shows the inertance in dB, right, the magnitude of the inertance in dB, and the lower figure shows the coherence, and the coherence, as we know, it varies from 0 to 1. So from the coherence plot we see that the coherence is much less than 1 at several frequencies. For example, it is not good at resonance frequencies as well as around the resonance frequencies, right. So we can see, for example, here the coherence is very not good. Similarly, coherence is not good in this range, right, and also at anti-resonance frequencies here also it is reducing, correct. So overall the coherence does not look so good, okay, and the FRF also seem to have some errors. For example, at the resonances there is drop in the FRF magnitude, right, so which is something unusual. So that is happening because of leakage which happens when the DFT of a random signal is taken, and that is why we see that there is coherence is also not so good and the FRF does not seem to be so accurate. So let us now use a window function, okay, to reduce the leakage. So we decide to use a Henning window function, okay, and the Henning window function is shown in the figure here. So over a record length of 4 seconds, so the Henning window essentially tries to force the signal to 0 at the starting and at the end points of the record length. So now what is done? The measured force and acceleration signals, they are multiplied by this Henning window, and then the process of estimation of FRF is carried out. So let us look at again the force and acceleration, right, after the Henning window is applied. So these are basically the force and acceleration time histories after the window function has been applied, and we see that now the Henning window has forced the force and acceleration signals to take 0 value at the beginning and at the end of the record length. So let us now look at the point inertance and coherence after the window has been applied and at the end of spectrum averaging. So you can see these are the results. Now we see that the coherence is much better, right, coherence is much better except at resonance and anti-resonance frequencies. For example, at the resonance frequency the coherence has dropped, and at the anti-resonance frequencies also coherence has dropped, right. But apart from that the coherence is good, it is almost equal to 1 in the rest of the frequency range, and FRF also now looks to be very good, right. So, it overall amounts to a good measurement. Now, the question arises why the coherence is poor at resonance and anti-resonance frequencies. So, at anti-resonance frequencies the signal level is very low, right, response is low, and that is why the signal to noise ratio would be poor at the anti-resonance frequencies, which leads to poorer coherence at anti-resonance frequencies. But what about resonance frequencies? Why coherence is not good at resonance frequencies of the structure? To understand this, let us look at the auto spectrum of the force, right. So, let us look at this. So, we are now going to see the auto spectrum of the voltage input to the exciter, and we are also going to see the auto spectrum of the force transmitted to the structure and overlaid on the FRF of the structure, right. So, these are the plots. So, on the left hand side we are looking at the auto spectrum of the voltage input signal, and because it is a random voltage input signal corresponding to 400 hertz, we see that the input voltage magnitude is roughly constant over this whole band. That is what we expect. Okay. The signal will have, the random signal over 0 to 400 hertz will have a roughly uniform magnitude over the whole range. On the right hand side now we see the auto spectrum of the force transmitted to the structure, right, shown in the blue. So, you can see this is the force on the structure, okay, and the red one is the FRF of the structure which we measured, and what we see that where the resonances are there, these are the structural resonances, right. So, at this frequencies, all these frequencies, the force magnitude drops significantly because of the force dropout phenomena we studied earlier, and because of that the signal to noise ratio for the force signal is not so good, right, and because of that the coherence drops to lower values at these frequencies. Okay. So, the coherence at the resonance frequencies of the structure drops to low values. So, therefore, having coherence less than 1 at resonance and anti-resonance frequencies is something that is expected, and therefore, the FRF that is measured still can be considered as a good estimate. So, in this way now we measure the FRF at other test points, right. So, we shift the accelerometer to other test points and repeat the process to get the FRF. So, some of the important characteristics of the FRF measurement if with random excitation signal are as follows. The estimated FRF corresponds to a linear approximation of the structure. This is because the force magnitude corresponds to a broad range of force amplitudes. Okay. So, so correspondingly the response also is in the broad range, it varies from low response to a high level of response, isn't it, and therefore, if there are any non-linearities in the structure, then this non-linear response will be averaged out, because you will also have a lower response as well as higher response at certain frequencies, and therefore, some kind of averaging will occur, and at the end the FRF that we obtain will correspond to a linear approximation of the structure. So, that is an advantage, right, that we are able to obtain FRF corresponding to a linear approximation of the structure. But one disadvantage is that the finite length of random signal suffers from leakage, okay, because the periodicity assumption which is there in the DFT, that is not satisfied, okay. So, because of that the leakage occurs, and hence use of window function is necessary with random excitation signal, and use of window function then distorts the signal. As we saw, the force and excitation signal, they are distorted when the window function is applied. So, although the leakage is reduced, but there is also some distortion in the process that is inevitable. Also, we require a large number of averages to get a good quality FRF. So, this also therefore requires a long time for the test. So, the test time becomes longer. So, in this way today we looked at FRF measurement using random excitation signal, right, and now we stop here. Thank you.